Welcome, everybody. Let me first thank you all for coming, either in person or remotely. I hope everybody's okay, as well as okay can be in these times. We're very pleased that Nuno came to us this week from MIT, where he is the director of the Plasma Science and Fusion Center, PSFC. You know that his PhD is from Portugal at the IST, and then spent postdoc appointments in Princeton at the Fusion Center, and then went back to Portugal to lead a research group before starting his position at MIT, where he now is a very, very accomplished scientist in plasma physics. He won the APS Award for outstanding contributions as an early career plasma physicist. If you wonder what he does for a living, he solves a very, very old problem about magnetic reconnection. The question is, how do magnetic fields dissipate energy? Then if you look at astrophysical plasmas, also how do you accelerate particles? So what actually makes many of the processes in the universe shine? Nuno has made really fundamental contributions to this problem. He works on effective new instabilities, plasma instability. Now, if you look into any physical simulation we do, is we really work analytically, simulation-wise, work on turbulence, on magnetic field generation. The universe is really relying on this. He's an expert on the subject. Today, initially, as you saw in one of the early announcements, I wanted him to talk about this today, but then he came around and was like, no, this context really is a big thing here. Many people do quantum computation. So he has a second passion that he's been working on over the past few years about how can you actually leverage in the future or even now quantum computers and how to design algorithms to solve physics. He's already worked on this new and emerging technology, and that's what we're going to talk about today. Thank you. Take it away. Appreciate it. Thank you. Wonderful introduction. Thank you, everybody, for being here. I understand these are times of stress for this community. I hope everybody's as okay as they can be. Thank you for showing up in person. So this talk is going to be much more aspirational than my usual talks. I said that my main research line is actually not this. As I was telling John just 5 minutes ago, this is a recently acquired distraction, perhaps a midlife crisis or a post-tenure. I needed something different. So I started engaging in this topic and I found it very intellectually rewarding and very interesting, even if results are scarce, as you're about to see. Okay, so take this with a grain of salt and more in the spirit of entertainment than anything else. And it's, of course, very humbling to give a talk on computing in this match at all with that person looking up at me. So I'll try my best. Let me try to give you some context for how these words actually got to be in the same slide: quantum computing, plasma physics, and fusion. And once I've given you that context, I'm going to tell you a little bit about the efforts that my group has been developing along these directions and what the challenges are. The talk is sort of received for a broad audience, so I have some introductory material on plasma physics and the kinds of problems that we're trying to solve so that I can contextualize the challenge of computing. For those of the audience who know more plasma physics than I do, I apologize in advance, but I thought some context would be good. So things that are in the plasma physics sphere, one of them, of course, is fusion energy, which is these days in a stage of development and excitement. 5 years ago, you couldn't even dream that we'd be here. There's been some very significant scientific and technological breakthroughs that have been sufficient to generate a whole private fusion industry, which is very vibrant and doing very well and promising things. Of course, the part of mastering fusion as an energy source involves very difficult challenges in plasma physics. And so, of course, computation has played an enormous role in bringing us to where we are right now in the fusion sphere. I can talk forever about this. Another thing in the physics sphere is this idea that you might have tabletop particle accelerators. So by very clever uses of lasers shining on different objects, you can generate electric fields that are incredibly high amplitude in spaces of a meter. And this has been explored as an opportunity for particle acceleration for multiple purposes. Space weather is becoming ever more important. So understanding the Sun-Earth environment is a plasma physics challenge. Understanding the solar winds. Right now, it's actually a very exciting time as well. For this area where you have the Parker Solar Probe jetting to the sun and telling us all about the plasma that you find between here and the sun. So that's a very exciting thing. Then, of course, astrophysics. There's a great number of problems in astrophysics that are, even though people sort of almost think that plasma is a dirty word in the astrophysics world, these are by nature plasma physics problems. Magnetic field generation, magnification, cosmic acceleration, accretion jets. These are very difficult physics problems. And again, at the heart of all of these problems is very significant computational efforts that have brought us to where we are right now, but which is still insufficient in terms of what you can do with a computer, the exascale era and beyond. From the computational point of view, we're now in the exascale era. It's, of course, very, very exciting. People are excited about exascale and GPU architectures and all these things. But it doesn't take very long to make the argument that even exascale gets you nowhere nearer to where you need to be to simulate realistic system sizes or realistic emission parameters or anything like that. So as you start thinking about quantum computing for some of these plasma problems, it's important to be aware of what is it that we're trying to solve and what does it take to actually solve any of these problems. So in terms of physics, the kinds of problems that we worry about are very specific dynamic problems. Time evolution of highly nonlinear systems. Turbulence is the typical example. Whether you're in fusion or astrophysical plasmas, you always have to contain turbulence. And it's not just that the turbulence is there, it's the fact that turbulence actually decides the properties of your object. So everything that you're observing in that system is probably being regulated to some extent by turbulence. What's the solution procedure on a classical computer? You say, let there be this initial condition, I'm going to plug it into some set of partial differential equations, evolve this forward in time and see what I get. On a classical computer, you are all-powerful, so you have the fields evolving at every point as a function of time. You can do this. In some cases, you're only interested in the final state, so you're given an initial condition, and your goal is to find out what is the final steady state. But in some other cases, no. You actually are interested in the path that the system took to get from A to B, as well as the final state. Regardless of the application, this represents enormous computational costs. Today's state-of-the-art simulations typically use tens of millions of CPU hours. This simulation you see here is actually 200 million CPU hours. This is sort of the biggest simulation that's ever been done of magnetohydrodynamic, MHD turbulence. This took about a year and a half to run and another year to data mine and then write the paper. So this version here is, I think, the resolution of 64,000 squared by 10,000 grid points. So it's enormous. And basically, there's only one. And this statement that there's only one is probably going to remain true for the next 5 or so years. So we're at the stage where you can do one of these, and that's awesome, but you cannot do 10. And this is going to be true for some time. Yes, there's enormous value in being able to do one of these simulations, but actually what you need to do is many of these because you're interested in how things change depending on parameters. One of these simulations, interesting as it is actually not enough. But then you might also ask, well, this simulation was 200 million CPU hours. Is this simulation actually realistic? The answer is no, it is not. This is a three-dynamic problem just with magnetic fields. If you ask what is the Reynolds number of the actual system you're trying to study, it depends, but it's going to be in the order of 10 to the power of 10 to 10 to the power of 18. The number here is about 1,000,000, 10 to the power of 6. So you pray to the Church of Scientology and you say, well, do the 10 to the power of 15 Reynolds number, but I think this is big enough and that's what I can do. And invariably, the story of physics has been to discover that as you increase Reynolds numbers, interesting things happen that you didn't see before. So there's a lot to be said for where we are versus where we need to be realistic in terms of the simulations that we can do. The complexity of plasma equations. One question that comes up very often is, I'm a very unsophisticated plasma physicist in the following sense. Most of the type of physics problems that I work with are classical. So they don't have any quantum effects and they're not even relativistic. So it's all classical physics. The audience over there is much more sophisticated in terms of physics. Like they know about special relativity, general relativity. And so the question that comes up is how hard can that be? Why is it that you're not even worried about any 20th century physics, so to speak? The idea to have in mind is think of source terms. You couple that to Maxwell's equations because in the plasma you have electrons and charged particles. Their motion generates or changes the magnetic fields and electric fields actually impose forces. So to do this self-consistently, you have to couple to Maxwell's equations. We know how to solve these equations numerically, but the problem is that you can't do simulations that are large enough to actually address the actual environments that you're interested in. Now, actually, if that's all that there was to this, you'd be kind of okay. But in fact, it gets much worse. For a large set of problems we're interested in, the plasmas are actually weakly collisional. That means that you can't assume that they behave as a fluid. They are not Maxwellian. And so instead of doing fluid dynamics, you actually have to do a much more first principle thing. You solve the Boltzmann equation or Vlasov equation for the distribution functions of your multiple species, electrons and protons, let's say. So what does that look like? It looks like a 6D equation that I wrote here. In plasma physics, we call this the Vlasov equation, but just think of the Boltzmann equation. You're solving a distribution function f, which is a 6D object. It depends on position x, it depends on velocity v, and then it goes as a function of time t. And you have to couple that to Maxwell's equations self-consistently. If you thought that your computer was big enough to fit, let's say, a 1000 cubed for a 3D hydrodynamic simulation, if you now do 6D in terms of 3D, you quickly see that actually the biggest you can do is on the order of 50 grid points to the sixth power, 50 to the power of 6. That's nothing. A resolution of 50 grid points is pitiful. That's about the best that you can do. Quantum computing, a culture clash. This brings us to 2018 in the context of quantum computing for plasmas and fusion. Back in 2017 or 2018, the Department of Energy organized a series of workshops for all the subdisciplines that are in their portfolio related to fusion. I attended. There is a report that comes from this. This meeting combined experts from the quantum algorithm side with experts from the fusion side. There was an introduction where someone said, you know, fusion is very challenging computationally. You guys are always the top 3 burners of computer time in the best supercomputers that we have. That's understandable. It's a very challenging problem. We're hearing that there's this nascent technology, quantum computation, and we're thinking, can this be used to accelerate the pace of discovery in fusion? They said specifically, if we go to fusion people and give them a quantum computer, would you guys know what to do with it? And we said, no. They said, well, that's just as well because we don't have one to give to you anyway. But they also said it was actually interestingly urging them. They said, instead of waiting 10 years for quantum computing to be a reality and then start to think about algorithms, should we start now? So that 10 years from now, when they become a reality, we're actually ready to play. That meeting was intrigued by what was an obvious culture clash between the fusion people and the quantum algorithms people. It was clear that there were interesting communication barriers about what the nature of the problem even was and how you do this. I was very intrigued. Then I wrote a grant proposal and I started thinking about it. The search for quantum algorithms. What does it mean to say that you're going to solve it on a quantum computer? I came to this with a very naive expectation that there is going to be some speed up. I quickly understood from my colleagues on the quantum side that factors of 2 or 3 are not very interesting. We're talking about polynomial speedups or exponential speedups. That's the sort of thing that you want to do. My understanding of this at the time was limited. I understood that there were algorithms where there was provably exponential speed up, like matrix inversion, HHL, that could be useful. But that's not enough because at the end of the day, you're trying to solve nonlinear problems. Also, the question of if you could solve this partial differential equation, what is it that you're actually going to measure that is interesting to you? You're going to say, well, I keep measuring the solution at every grid point and get my velocity field as a function of position the same way that I do on a classical computer. That's probably not going to work. So, how is it that I recast the problem or think in terms of different variables or something that will still allow me to extract useful information? Maybe it doesn't make sense to think that the QC is going to replace the classical computer, but can I recast my problem so that I can use the quantum computer to answer questions that I can't currently ask with the classical computer? This is sort of an interesting paradigm shift. Specific approaches and mappings. 1. Linearization. There are efficient algorithms for some conditions like Hamiltonian simulation. There's a very famous problem in plasma physics called Landau damping. You take the Vlasov equation, assume there is a background distribution function, perturb it, study how that perturbation evolves. If you subject it to an electric field, you find that the electric field will damp. This is linearizing the problem. You can take this problem, cast it as Hamiltonian simulation, and show that for that particular problem you can get quadratic speed up. But this is the first example of thinking about this incorrectly. Instead of saying, here's the problem I want to solve, let me find a quantum algorithm for it, I did the opposite. I know what quantum algorithms exist. Can I find a problem in plasma physics that would be amenable? This is backwards thinking. It's a proof of principle, but you can solve Landau damping analytically, so it's not particularly useful. 2. Kohl-Hopf transformation. Consider the Burger's equation. It's not the Vlasov equation, but it has a nonlinearity term, u partial xu, and a viscosity term. It looks like many differential equations we'd like to solve. For this particular equation, it is known that there is a transformation called the Kohl-Hopf transformation. It maps that equation onto the heat equation. Now you're sort of happy because the heat equation is linear. You can solve that equation with some sort of matrix inversion algorithm, and presumably that would be efficient on a quantum computer. It would, were it not for the fact that the solution actually scales exponentially or polynomially as a function of time. But in principle, this is a way to map a nonlinear problem to a linear problem. But again, completely useless. The Kohl-Hopf transformation only works for this equation. If I give you a different PDE, you can no longer do it. It's a unique solution to a boutique problem. 3. Kármán linearization. This is a technique called Kármán linearization. You say, define a new set of variables, x sub n, which are powers of x. If you take this and plug it back in, you find the equation for x sub n is something like a coupled linear system. You've mapped one nonlinear equation onto an infinite coupled set of linear equations. This is exact. But you're inevitably going to have a truncation problem. You have to decide what to do with variable n plus 1. In general, there is no small parameter here. You can't guarantee that the truncation converges. We've done some work with this with Andrew Childs's group at the University of Maryland. We showed that for the discretized Burger's equation, Kármán linearization does lead to computational quantum advantage, but the convergence is only guaranteed if your nonlinearity is small, Reynolds number smaller than 1. Of course, what you want to do is large Reynolds numbers. 4. Madelung transformation, quantum hydrodynamics. You can do something called the Madelung transformation. When you do that, you work with a coupled set of equations like quantum hydrodynamic equations. These equations are actually similar to some fluid equations that you encounter in plasma physics. So there is a mapping. The idea is, if I have a set of equations that I want to solve, can I find a mapping that takes them to sets of equations that are better on a quantum computer? The Madelung transformation maps the Schrödinger equation to fluid equations. We coded it up on IBM computers and could actually simulate something that looks like a shock. You're not actually solving the fluid equations. You're solving the Schrödinger equation with the right potential that then maps to the fluid equation. 5. Inverse scattering transform, KdV. Another thing we thought about is this concept of inverse scattering transform, IST. This works for some cases of exactly solvable nonlinear equations like the KdV equation. You can map it to something that's a coupled set of ODES using the inverse scattering transform. Perhaps here you can have some sort of advantage. But again, the only thing that I've tested so far that's actually general is Kármán linearization. All these other methods are what maps do I know that take a nonlinear PDE and map it to something linear? 6. Koopman operator, stellarator optimization. This is actually a very interesting one and might be one of the very few problems that sort of almost straight out of the book seems like inherently a quantum computing problem. You take the MHD equations and say, here's a plasma state and I want to know if it's stable. You linearize those equations. The force operator is Hermitian. So in principle, this satisfies all the conditions that you would have for a normal quantum mechanical problem. Basically, can you find its ground state? If it has growing eigenvalues, it's unstable. This is a legitimate fusion problem. We do solve this problem on a routine basis. If you could have a quantum advantage and do this much faster, then you can start to try different topological configurations and try to optimize in that space much faster than you can do today. People in the fusion business play with this concept of a stellarator. A stellarator is a geometrically challenging device. It's a donut, but now you imagine that you section the donut in different sectors and you twist each one by a different angle. It has very interesting confinement properties, but as soon as you introduce this degree of freedom, you have an enormous optimization space. Finding the optimal configuration requires running calculations very, very fast. 7. Tensor networks. We've been working on this with a postdoc, Ira, who had a PhD here at Caltech in chemistry and then moved to MIT to work with me. She was an expert in tensor networks, which comes from many body simulation. It turns out you can use these same techniques to solve PDES. What we seem to have found is that these methods, which are quantum inspired, actually can have a classical advantage. For the KdV equation that Ira tried, you actually do faster calculations on a classical computer using these techniques. Summary and Q&A. Plasma dynamics is intrinsically nonlinear, very strongly nonlinear. Nonlinearity is everything. The reason we are where we are right now is largely through computation. But if all we do is brute force, 20 years from now, we're going to be talking about a simulation that's maybe 3 times larger, but 3 times larger is nowhere near where you actually need to be. Brute force alone is actually not going to get you anywhere in our lifetime. So you buy into algorithms, machine learning, AI, or something else. You have to think beyond brute force. We've been rethinking. How do we cast the problem? What is it that we actually want to measure? Question on machine learning. Question. There's a large set of problems that people are applying machine learning to. Is there an inventory of algorithms? Answer. If you're interested in plasma control experiments, machine learning has actually made a lot of impact there. Real-time monitoring of plasma. That's very useful from an engineering point of view. But if you're actually trying to learn physics, I'm not so certain. You can accelerate solutions, but you're doing this at the expense of a black box. I have yet to see an obvious application of machine learning that said, here's a physics result that I didn't know about, which I've been able to obtain because of this. Question on mappings. Question. Is there an inventory of mappings? Answer. My understanding is that right now there isn't a large inventory of quantum algorithms for which you can be certain that there is at least a polynomial speed up with respect to classical for non-linearities. Short of finding mappings, I'm not sure how you actually address this problem. Kármán is the only general-purpose mapping I know, but it's limited to weak nonlinearity. Closing thoughts. If quantum computers are going to be useful for science and engineering at large, you kind of think that you'd have to be able to solve nonlinear PDES because that's what everybody does. It feels to me like a very fundamental problem. On hybrid algorithms. Hybrid algorithms, quantum classical, will be very challenging for a problem like this. If you say, I do the linear part on a quantum computer and the nonlinear part on the classical computer, The reason is that at every time step you'd be reading and then reloading. Preparing the quantum state, reading it, and doing it again is very inefficient.